In this video, we're going to go over a couple problems using the disk method of finding volumes of revolution, probably in a calculus class here. First problem, we're going to find the volume of the solid that is generated by revolving the region in the first quadrant that is bounded by y equals x squared, x equals 2, and y equals 0 about the x-axis. First thing I'm going to do here is kind of get a picture of what's going on. So I'm going to sketch this here, and then I'll have a nicer picture in a bit. So I'm going to just draw some axes. Whoops. Y equals x squared. It's going to look like this. X equals 2. It's going to be some line here. Vertical line. Y equals 0. That's the x-axis here. Y equals 0. So the region that's bounded by these is actually these, or this region here. So we're in the first quadrant as well. So we're going to take that region here. Let's get a sort of a Mathematica view of that region. It's going to look a little bit nicer. So here's our Mathematica view here. What we've got is this shaded blue thing. We'll talk about this red line in a bit here. So what that red line is we're rotating about the x-axis here. So that was really that red line. Whoops, get the red line in the Mathematica drawing. So this is really our axis of revolution or rotation. Sometimes I'll try and put a little arrow there to maybe denote, oh hey, we're actually rotating about that line here. So what we're going to do is take this shape and kind of spin it around. If we had sort of a red, I don't know, pole here that we're going to spin this around on. And the question is, what will it create? So if you think about that, it's going to be kind of, I would say, sort of the horn of a trumpet kind of shape, but I can actually show you the Mathematica picture. So here's the Mathematica picture, and I've got that axis of revolution essentially drawn in here. And I've got a little bit different XYZ thing going on here. We can get an idea of the shape with that axis of revolution here. When I rotate it around, I get this sort of, I don't know, horn-looking thing. Now, to find the volume, essentially what we're going to do is approximate this volume of this shape with some cylinders. So the disk method, well, disks, but they're going to be cylinders here. So picture that here, just to get a sense of what's going on, is this here. So we've got a bunch of cylinders, and this should give us essentially the shape we have here. So if you did more and more cylinders, you could stack them together and get closer and closer to being sort of a smooth curve here instead of this kind of jagged thing we have here. So you get a bunch of these little cylinders here. So our goal when we find the volume is we're going to try and essentially find the volume of each one of these cylinders and then add them all together. Okay, so that's the idea. Then what we're going to do here is one of our cylinders, let's just draw, how about a green rectangle here. We're going to take this green rectangle and rotate that about the x-axis, and that'll form a cylinder. And the way this is oriented, if you rotate around the x-axis, that sort of cylinder is going to be a disk sort of in this orientation as well. So like this, maybe green one there, or green one there, or it doesn't have to be green. Okay, so what I'm going to think about here is my volume, well, is approximately the sum of all of those disks here. So I'm going to do a sum, whoops, it's supposed to be sigma notation. So sum, I could worry about index bounds here, but I'm not actually even going to do that. I'm going to do a sum of the volume of one of these cylinders, or volume of each one of the disks. So this is going to be volume of a disk. And then the idea is you add up the volume of all the disks, should give you an approximation to the volume of the solid revolution. And then as you get more and more disks, you let the sort of height of the disk go to 0. That's going to make this sum turn into an integral, and we actually get a volume equal to the integral. Okay, so what we need to do is find the volume of a disk here. So to do that, we're going to use the volume formula for a cylinder. So volume for a cylinder should be pi r squared times the height. Now, because this volume is sort of one of the slices here, so one of the slices that we do in this, generally I'm going to write delta V here to sort of say it's the small slice of the volume here. And what I'm going to think about is that rectangle. Let's just draw this green rectangle here much bigger. When I rotate that around, maybe I'll draw my axis of rotation here. When I rotate that around and I get a disk, what I'm going to get is this distance here will be the radius of the disk once I rotate it around. This distance here is the height. Now, notationally, what we're going to do is this distance here, it's that small distance between there, that's going to be delta x. So our height is delta x, so it's sort of the change in the x value. The radius is going to be the height of the function sort of when x is x. So if I fix an x, the radius is going to be really the height of the function. Well, that's y equals x squared. That's just going to be x squared. So our radius will be x squared when sort of our x value is x. So our delta v is going to be pi. Our radius is x squared squared. Our height is delta x. So if we go back over here to our volume, that means our sort of summation is a summation of volume of a disk. We're just going to put in a pi x squared squared, that's x to the fourth, and we get our delta x. Now, what that means here is this is really an approximation to the volume. So the true volume will be, suppose we had 50 or 100 or a billion of those coins here, so they all get really, really thin, and that's going to turn into an integral, sort of via a Riemann sum. So we're really going to integrate pi x to the fourth. The delta x becomes a dx. And then we have to think about what our x bounds are. If we go to our graph, x can start at 0, be anything from 0 to 2. So we're just going to get bounds of 0 to 2. So we wrote down an integral that will give us the volume of revolution. Now, let's evaluate this. So I can pull the pi out. Antiderivative of x to the fourth is x to the fifth over 5. We just evaluate from 0 to 2. I could write this as pi over 5 times 2 to the fifth minus 0 to the fifth. Well, that's pi over 5 times 2 to the fifth is 32. 0 to the fifth is 0. So I'm going to end up with 32 pi over 5 as our volume. So that tells me here that this shape up here, this shape, if we filled this in, would have volume 32 pi over 5. You can get a sense. Whoops. There you go. Maybe a better sense of what that shape is if we rotate it around a bit here. So essentially I just took that. Here's our y equals x squared, and we just rotated that around. Next problem. Another disk method. We're actually going to take, if you read this, it's the same region, but now we're going to revolve about the line x equals 2. So what's going to change here, let's draw our region again. We have like a y equals x squared. I messed that up. About y equals x squared. And then we have an x equals 2. That's one of our bounds. This is our region. But we're also going to now rotate about this line here. So we're going to rotate maybe in that direction, although it's hard to draw that. So we're going to sort of rotate horizontally instead of vertically, perhaps, the way it's drawn. So pictorially, down here, here's our region. Same region as before, we're just rotating about this side instead of the other side. When you do that, you'll rotate it around this way, and what you'll get is, again, it kind of looks like a trumpet, sort of bell of a horn kind of thing here. But it's going to have a slightly different shape than before. So it's rotated 90 degrees, I suppose, but it's also going to have a somewhat different shape. So that's really what we're going to get. Very similar to what we had before, but a bit different. And we're going to, again, approximate this by doing a bunch of slices here. And the way our slices work, the red, again, is the axis of revolution. Kind of see the axis of revolution here. Our slices here sort of go, along the axis of revolution here. So you kind of just approximate this sort of bell shape with a bunch of disks here, or coins maybe makes more sense to call them. And if you got more and more and more of these disks, you get a better and better approximation. So we can do the same thing here. So our same thing as before. Our volume, we can approximate with a sum. That sum is going to be, let's just draw a rectangle here. Now, because we're rotating about a vertical line, our rectangle that we're going to rotate about, let's do this in blue, is actually going to be a horizontal rectangle. Let's see if we can draw that a little bit more nicely there. Whoops. So worried about that. There's y equals x squared. our rectangle is going to go this way, and we'll rotate it around, and we'll get disks really that are sort of flat in this direction. So they're sort of 90 degrees from where they were before, because we're rotating about a vertical line instead of a horizontal line. So the volume when you rotate this around, let's draw this big here. We're going to rotate about this line here. And so when you think about what's going to happen in terms of the radius and the height of the disk, which is really a cylinder, this distance is the radius, and this distance is the height if you rotate this around. Okay, now our height here, that's going to be really the change in y. So now we're going to have to fix a y, and because we're doing sort of a horizontal rectangle here, we're actually going to get a delta y, and we'll want the rest of the formula for the volume in terms of y instead of x. So this will turn into a dy integral. So we're going to get a pi, and then it's just going to be the radius squared. So the radius is this distance here. Well, what's that? Well, the right endpoint is 2. The left endpoint, so this is 2, is this function here. That function is y equals x squared, but we'd like to get a formula for the x value. It tells me sort of the horizontal distance in terms of y. So that function, y equals x squared, that's also x equals square root of y. So what we'll get is our right bound is 2, our left bound is square root of y. That means this radius is actually going to be 2 minus the square root of y. We're sort of at height y. Here, so we take the right endpoint minus the left endpoint. So what I get is 2 minus square root of y. Then I have to square that. Now, so this is our sort of, each one of those disks is in the blue here. We add all those up. That gives us the volume. So the true volume is going to be an integral, pi times 2 minus square root of y squared. The delta y will turn into a dy. And then our bounds on y, well, this point up here has x2. That's going to be y equals x squared. Y will be 4. So y is actually going to go 0 up to 4. So the possible y values go from 0 to 4. And when we do this, I'm just going to sort of expand out this 2 minus square root of y squared. So I'll get pi times the integral 0 to 4. When I square this out, 2 squared is 4. 2 times square root of y is 2 square root of y, but then I have to double that. So I'll get 4 square root of y. And then I add square root of y squared. That's just y. So I get this integral. So I get pi. So we can do our antiderivatives. Antiderivative of 4 is 4y. Antiderivative of 4 square root y is 4y to the 3 halves divided by 3 halves. Antiderivative of y is y squared over 2. And we're going to evaluate those going from 0 to 4. So evaluate at 4, subtract, evaluate it at 0. So that's going to give us pi times, so we plug in the 4. 4 times 4 is 16. This 4y over 3 halves. Dividing by 3 halves is multiplying by 2/3. So we get a minus 8/3. 2 times 4 giving me the 8. Now 4 to the 3 halves might be worth talking about here. Let's do this off to the side, I suppose. So when you have 4 to the 3 halves, I'm going to think about that as 4 to the 1/2 cubed. 4 to the 1/2 is square root of 4. So that's 2 cubed. That's 8. Here. So 4 to the 3 halves gives me 8. That means that this y to the 3 halves will actually give me an 8 there. And then I'm going to add, let's see, y squared is 16 over 2. I suppose that's an 8 as well. I should be subtracting, plugging in 0 for y, but each of these terms is 0. So let me write a minus 0 here. They're all 0 when I plug in 0 for y. And so what I get is pi times, let's see, 16 plus 8, that's 24, minus 8 times 8, that's 64/3. And I can rewrite this as pi times, let's see, 24 times 3 is 72. So that's 72/3 minus 64/3. So I get my pi times 8/3, which I'd probably write as 8 pi over 3. So a different volume than we had before. I believe it was 32 pi over 5. We rotate it around the other axis. 32 pi over 5. So slightly different volume, which maybe is a little bit surprising here. But this is really our quick sort of introduction to using the disk method. Things that we'll worry about later on here. Let's talk about this. When we do washer, that would be like you rotated about the line, say the y-axis here. So if we did a washer, let's just redraw this, and we're not going to calculate these. Let's talk about the other methods here. So if you do washer, let's just say we're not going to calculate them now here. You do washer, what you're going to get is I take my parabola, my region like this, and I might rotate about a line like this here. And then I can draw the same rectangle, but now when you rotate that around, what you're going to get is really a washer. So the top view is going to be a circle. It's a pretty bad circle. Circle like this, maybe an outer circle like this, but with a hole in the middle, it's going to have very minimal sort of height here. So that'd be a coin with a hole in the middle, let's say a washer here. And these distances, just sort of visually, this distance here, that's really the hole. So that's from the center to the hole. The axis is really in the middle here. And if I wanted to do, how about this distance all the way out there, that's really from the center out to sort of the complete outside. That's sort of what's going on. You could then find the area of this circle with the circle cut out, and that would give you, multiplied by the thickness, which I guess would be delta y in this case, would give you a volume, and you can play the same game we just did. So that's washer method. Just a rough rundown. There's also something called the shell method. So what the shell method would do, let's do the same drawing here. It's a completely, well, it's a different method here. So let's do our graph, and let's rotate about the y-axis here again. Now, this time, what you're going to do, let's pick, how about green? You're going to take a vertical slice here, and when you rotate that around, you're really going to get, like, think like a tin can with no top and bottom. You're going to get a shell here. And so you'll rotate that around, essentially take a piece of paper and roll it up here. So you get really thin layers there, but you'll get sort of a, let's see if I can draw this, something that looks like this, but then a really thin area like this. And it's going to sort of rotate around here, rotate around here, go down. And so that's probably a pretty terrible drawing of a shell here. So we'll get to eventually talking about those methods, get some Mathematica drawings that are much better than what I'm trying to draw here. But to give you just give you a sense of sort of what else we can do here.